Hello everyone and welcome to day 35 of Jamb Physics in 40 days. I want to say a big thank you to all of you who have always been part of the series from the beginning, from being with us from day one. This is day 35 and in just a few more days the entire series will be over. I want to believe that you've been gaining a lot from the series. Please drop us a comment based on your experience on the series so far from day one. We would like to hear from you, and we also like to hear of your experience with the Exam Phone app, and of course how you've been doing in general with the Jamb Physics series that we've been doing so far. And I want to say thank you for also subscribing to the channel and also sharing the content and liking the videos. Please, if you are yet to be subscribed to the channel, kindly take a moment to click the subscription button and also the notification bell icon so that you get notified every time we put out a new video. Now, if you're seeing this video for the first time, this is Jamb Physics in 40 Days, a series that is brought to you by Learn. We would believe that when you dedicate within 30 to 45 minutes of your time daily, you should be on your way to get all the necessary skills and tools that will help you ace Jamb Physics. So if you are preparing to take the Jamb exam anytime soon and one of the subjects you have selected is physics, then believe me, these videos are made specifically for you. So trust me, you don't want to miss any of the videos in this series from day one to the end, so please check them all out. What we've been able to do is that in each of the videos, we take a look at the individual topics that are in the Jamb Physics curriculum, and then we do a breakdown of what is expected of you as regards those topics, and then we go on to solve past questions on those topics, and then we give you some tips that help you solve that question and any other question like that based on that topic with great accuracy anytime you find such kind of questions. So basically, if you're able to look at all the videos from beginning to the end, nothing should be able to stop you from scoring 90 plus in Jamb Physics. And I believe you want that for yourself. So please check out the videos from day one and please ensure that you click the subscription button and be subscribed to the channel. You can also click the notification bell icon so that when the next video comes out, you will also be notified. And please, we are trying to reach a wide range of audience and you can help us to achieve this by sharing the video. So when you watch the videos, ensure that you also share them to those on your timeline so that they too can be exposed to videos like this. Many people don't know that this is going on, so please keep sharing until we reach as many as possible. And I want to say thank you because I know you are doing this already. And one thing that I can also help you improve better is more practice, and so you can download the Exam Phone app also, and the link to download is in the description box of this video. The app is created in such a way that it makes your learning experience fun, in the sense that it covers a wide range of subjects and topics, and then you get to answer questions at levels where you score points. And what's interesting is that you can also earn some money as you answer questions. So it is the app that I call the one that is both exciting and rewarding. So if you want to enjoy your learning time, you can do that with the Exam Phone app. It is exciting, it is rewarding, and trust me, you will not regret downloading the app. So click the link in the description box to download the Exam Phone app today. Now, what we are doing in day 35 is electromagnetic induction. Now, the subtopics under it are listed here, and this is what is expected of every candidate to cover as regards the exams. They expect that you should be able to state the Faraday's law of electromagnetic induction, both the first law and the second law. Remember that the first law tells you that when you have a magnetic field interacting with an electric field, a current is induced, right? And then the second law tells you that the magnitude of that induced current depends on the strength of the field. So you see there, it's important that you are able to state the law, not just in this simple term that I've just done, but in actual details. And there are, of course, some points that you should be able to pick out. As we solve questions, you will find such like that, and then I'll begin to give you some points that you should always keep in mind when answering question on Faraday's law of electromagnetic induction. Now, as regards the factors that affect the induced EMF, one of them is the strength of the field. It affects the amount of current that is induced. Another thing that affects that is the velocity of the motion, right? The faster it is, the more current that is induced in such a linkage between the electric and magnetic field. Another thing that can affect the induced current is the number of coils. So that is also very important to determine the induced current in an electromagnetic field. So you should be able to state all these factors that affect induced EMF, and also state the Lenz's law, and also differentiate between the AC and DC generator. Now, we have mentioned some part of this, especially with the Faraday's law of electromagnetic induction, and we have solved some questions that are linked with it, even in tiny details in the subsequent videos we have done before, the ones before day 35. But in this video, we'll touch them also, as well as transformers. Now, we'll be dwelling a lot on transformers, induction coils, inductance, and eddy current. I should be able to tell what a transformer is, the type of transformers also, that is the step-up transformer and the step-down transformer. Now, you should know that a transformer is able to transmit power from one circuit to the other by relying on electromagnetic induction. So there is no direct link between the two circuits, but it's able to transmit the power from one circuit to the other, that is from the primary coil to the secondary coil, even though they are not in direct contact. It does this by relying on electromagnetic induction. And you should know that for an efficient transformer, the power in the primary is equal to the power in the secondary, which is very hard to create due to some defects that can occur in transformers, such as eddy current losses, loss due to hysteresis, and the likes like that. So you should be able to state those factors, and you should be able to calculate the efficiency of a transformer. Now, after that, you should also be able to do calculations on induction coil, calculate their inductance and the likes, and you should also be able to explain eddy current. So these are what is expected of every candidate on electromagnetic induction. Now, this video is made specifically for those preparing for Jamb. So the details involved in all of these subtopics that I've mentioned, you'll find those in another video on the channel on electromagnetic induction. So you can find the playlist where we have electromagnetic induction, and then go through the series of videos we have there that explains this in more detail. The laws are stated there and they are explained. And then we also go on to the factors, the Lenz's law, everything that I've just mentioned there is there, but in greater detail. And we also solve questions there, many examples, and then we highlight, also give you tips on how to know what to do when you find a question on topics like this. But for the purpose of this video, what we are going to be doing is we'll be looking at some Jamb past questions on electromagnetic induction, and then we get to solve them. And then while we are doing that, I'll be giving some tips also that will help you solve questions like that, and then also questions that may look like that or that are in the same direction as the questions we are solving. And I'll be handing those tips so that you'll be able to solve those questions with great accuracy anytime you find them. So if you're ready, get all your materials and let's solve some questions on electromagnetic induction. A transformer has 300 tons of wire in the primary coil and 30 tons in the secondary coil. If the input voltage is 100 volts, the output voltage is... Now, before I solve this, let me also mention this tip for you. When you see a transformer like this, where the primary has more tons than the secondary, that is, in this case, you see the primary coil has 300 tons, while the secondary coil has 30 tons. That tells you that this is a step-down transformer. That is, the input voltage will definitely be more than the output voltage. Now, conversely, what that means is that the input current is going to be less than the output current. Remember that the power in the primary equals the primary in the secondary for an efficient transformer. So you have to apply that. And power is current times voltage. Okay? But to solve this question, we're going to be relying on the relationship between the number of turns and the electromotive force in primary or secondary circuit of a transformer. Now here is the equation that joins all of that together. Now the equation says number of turns. Now it depends if you want to start from primary to secondary or secondary to primary, it doesn't really matter. But if I say number of turns in secondary over number of turns in primary, now this equals the electromotive force in secondary over electromotive force in the primary, like that. But by the time I get to current, it will be current in primary over current in secondary. So take note of this. You see that depends on how I start. If I had flipped this and say number of turns in primary over number of turns in secondary, I'll also flip this and then I'll also flip this. So it all depends on what is at the numerator. For number of turns, if you have secondary over primary, for electromotive force, it will also be secondary over primary, just like the number of turns. But for current, to be the inverse, that is, it will now be primary over secondary, just as we have it here. So since we are looking at just the output voltage, I'm only going to limit it to this side of the equation. So number of turns in the secondary is 30 over number of turns in the primary, 300, equals E of S, that's what we want to find, that's the output voltage, over input voltage, which is 100 volts. So from here now we can then say ES equals 100 volts times 30 over 300. So 0 cancel 0, 0 cancel 0, 3 here 1, 3 here 10. So 1 times 10 will give us 10 volts. So the correct answer here is option B. How can energy loss be minimized through eddy current? Now, eddy current losses can be minimized by laminating the core of a transformer or by thereby increasing the resistance of the core material. So the correct answer here is option A. You see what we have in option B, which is by using insulated soft iron wires, is related to reducing hysteresis loss. So this is for hysteresis loss, while this is for eddy current loss. So the correct answer remains option A. Efficiency of a transformer is equal to, now when you're asked to calculate the efficiency of a transformer, is often given as IS VS or ES over IP VP multiplied by 100%. Now, note that IV is power. And the S's we have here, this is for secondary, while this is for primary coil. So that is the power that is developed in the secondary coil divided by the power that is given to the primary coil, that is supplied to the primary coil. When you find the ratio there, you multiply by 100, and that's how you get the efficiency of a transformer. So that is the correct option to answer this question is in D. The strength of an electromagnet increase with, now option A say increase in the number of turns of the coil. B says decrease in the current with the coil. C says increase in the distance between the pole. And then D says increase in the current without the coil. Now option D does not even make any sense in this context because of this without. So we can cancel that out. So it's not the correct option. Option C says increase in the distance between the pole. As you increase the distance, it weakens the electromagnet, so it does not go in line with what we have, since we want an increase, right, in the strength, not a decrease. So that means this is not correct as well. Now option B says decrease in the current with the coil. Now when you decrease the current in the coil, it weakens the electromagnet. So the strength of the electromagnet would therefore decrease as well. So that is option A is the only correct option here. And it is increase in the number of turns of the coil. So we go with option A. Induced EMF are best explained using, now when it comes to induced EMF in electromagnets, there are two laws that talks about this. We have the Faraday's law of electromagnetic induction and we have the Lenz's law. Now, of these two laws, Lenz's law is only telling us about the direction of the induced current. Well, this is supposed to be option D. So it's only telling us the direction of the induced EMF, but Faraday's law directly links the EMF induced to the change in magnetic flux. So that gives you more detail about the induced EMF. Now, some might get confused and say, but the Faraday's law stated here is not specific in the sense that they didn't say Faraday's law of electromagnetic induction. Could have meant Faraday's law of electrolysis, because there are, of course, two significant Faraday's law when it comes to physics, that of electrolysis and that of electromagnetic induction. But because of the context of this question, induced EMF are best explained. So even though it is not specific here, we have to take it as Faraday's law of electromagnetic induction, and it explains more about the induced EMF as compared to Lenz's law that only gives you the direction of the induced EMF. This tells you about the magnitude of that induced EMF. So the correct option here is therefore B. If you're still not subscribed to the channel, kindly take a second to click the subscription button and also the notification bell icon so that you can get alerted every time we post a new content like this. And don't forget that you can always ask your questions if there's anything you'd like to ask us, or if there's something you found during your study time that you need some help with. Kindly put it in the comment section and we promise to attend to all of your comments. And don't forget to like the videos as well as share them on your timeline to help us reach many students who are in need of content like this. Now, this question says, what is the inductance L of an inductor whose reactance is 1 ohms at 50 over pi hertz? Now, when it comes to inductance of an inductor, there is an equation that links inductance of the inductor with the reactance of the inductor. So what we apply is reactance of the inductor, known as inductive reactance, equals 2 pi FL, where F is the frequency of the circuit and L is the inductance of the inductor. Remember, this is the inductive reactance. Now, the inductive reactance is the resistance offered by an inductor in an AC circuit. So in this case here, the reactance rather is given as 1 ohms. So we say 1 equals 2 pi multiplied by F. Now F is 50 over pi, and then all of this multiplied by L. Since we're asked to find L, we can see easily that pi cancels pi, and then 1 equals 100 L. Since 2 times 50 will give you 100. So the inductance L is therefore 1 over 100, which is 0.01. Now, inductance is measured in henries with the symbol H. So that is 0.01 henries or 0.01 H. So that is the correct option here is B. If a charged ion goes through combined electric and magnetic fields, the resultant emergent velocity of the ion is, now let's derive the equation for this. Now, we already know that F equals QVB, where this is the charge, where this is the velocity, and this is the magnetic flux. So, having known this, we also have to find an equation that connects F and energy. So, energy is supposed to be the force divided by the charge, which implies that F is QE. Okay, so now all I have to do is equate these two things since they all tell us about F. So if this is equation 1 and this is equation 2, I can equate 1 and 2 such that QVB equals QE. So from here we can see immediately that when we want to make, remember the question is telling us the velocity of the ion, right? So making V the subject, V would then be QE divided by QB. So Q cancel Q. So what we have is E over B. So the correct answer is E over B, which is option A. The core of an efficient transformer should consist of laminated pieces of metal in order to. Now, if you've gone through the studies of transformers, you realize that what some of the defects that you can have in a transformer are the eddy current losses, and then secondly the hysteresis losses. Now, when it comes to the eddy current losses, this is when the eddy current is generated in the transformer, leading to much heat that leads to power loss or energy loss, which we can calculate by I square R, of course. So as the heat increases due to eddy current, energy is lost in the transformer. So in order to reduce this, the core material is made with thin laminated material in order to reduce eddy current and at the same time reduce the heat that leads to energy loss. So it should be reducing heat and reducing eddy current. And the part that says that is in option D, which says reduce the heat produced by reducing the eddy current. So that will be the correct answer, option D. A step-down transformer has a power output of 50 watts and efficiency of 80%. If the main supply voltage is 200 volts, calculate the primary current of the transformer. Now, to solve this, I did mention at the beginning of this video that to find efficiency of a transformer, efficiency equals power output over power input times 100%. Okay, now we should note power output is current in the secondary multiplied by the voltage supply at the secondary, the voltage given at the secondary coil, while power input is IPVP. This can be written as E instead of V as well. So in case you find equations like that, we are still talking about the same thing, which is the EMF or the voltage at the primary or the secondary, where P is the primary, S is the secondary. So if we apply that here, we can then say the efficiency, since it's 80%, we can bring this 100 here and then say 80 over 100 equals power output of the transformer is 50 watts. Now divide that by power input. Since we already have the voltage, we just need to find the current now. So current in the secondary times 2, in the primary, times 200. So from here now we can then cross multiply. So we would have IP equals 50 divided by, this is 0.8, so that will be 0.8 times 200. So easily we can say 0 here cancels 0 here. So what we have now is 5 over 0.8 times 20. So let's multiply through. This would give us 0.3125, thereabout. So when we look at the options we have 0.31 and the others are 3.2, 3.4, 5.0. So that means the answer here is approximately 0.31. So we go with option A. Remember, it's in amperes. Lenz's law is the law of conservation of what? Now, when we consider Lenz's law, we see that it is showing that the magnetic induction is conserved, and that is a form of energy. So what is conserving is energy. So we say Lenz's law is a law of conservation of energy. So we go with option C. The main purpose of the transformer in an AC radio set is to, now, in an AC radio set, that tells you that it requires AC power to function, but the transformer is still in it. So let's look at which one of these options is the purpose why a transformer is put into an AC radio set. So option A says increase power to the radio. Now, transformers do not increase power. It's the same power that you have at the input that you also have at the output. It only transmits power through electromagnetic induction. Okay. Now, option B says step up the voltage. Now, if you should step up the voltage more than what it was at the primary, I'm pretty sure the radio set will be damaged. It requires lesser voltage than what is at the primary. Now, C says to convert energy from AC to DC. Now, this is not done by a transformer, but done by what is known as the rectifier circuit. But when we get to semiconductors, we'll talk more on rectifier circuits and the likes. But we know this is not for a transformer, but for a rectifier circuit using diodes. And then option D says to step down the voltage, that is, reduce the voltage from the primary to what we have in the secondary, which is much smaller than what was in the primary. So the correct answer here is D. A 2 Henry inductor has negligible resistance and is connected to a 50 over pi hertz AC supply. The reactance of the inductor is, now reactance XL is 2 pi FL. So let's solve for XL. That will be 2 pi multiplied by the frequency, which is 50 over pi, multiplied by the inductance, which is 2 henries. So now we see here that pi cancel pi, right? 2 times 50 is 100. 100 times 2 will give us 200. So XL is 200. And reactance is measured in ohms. So 200 ohms, which is option A. The principle of operation of an induction coil is based on, now the induction coil works by increasing the voltage supplied to it by applying an electromagnetic field. That is, it depends on electromagnetic induction. And the law that we use whenever we're explaining electromagnetic induction is known as the Faraday's law of electromagnetic induction. So that is, the principle of operation of the induction coil is based on Faraday's law. So we go with option C. A transformer has a primary coil of 500 tons and a secondary coil with 2,500 tons. When the voltage input in the primary coil is 120 volts, the output is, so let's put out what we have from the question. The primary coil, number of turns in the primary is 500, and then number of turns in the secondary is 2,500, and then the input voltage, that is at the primary coil, we have 120 volts. So we are asked to find the voltage at the secondary. So in order to equate, the equation that combines these four things here says that we should have number of turns in secondary over number of turns in primary, and equate that to the voltage in secondary over voltage in primary. Now, if you are working with current, however, you know that you have to flip it. It will be IP over IS on the other hand. But since you are working with voltage, we just go on with this. So what we have as NS is 2,500 over NP, which is 500, equals ES over 120 volts. Now, what this means is that ES equals, now when you divide this, you get 5. So multiplied by 120 volts, and this would give us 600 volts. That is, the secondary voltage or output voltage is 600 volts, which is option B. The best material for the core of the primary and secondary coils of an induction coil is, now for an induction coil to work efficiently according to the law of electromagnetic induction, it requires a rapidly changing magnetic field. So meaning you need a material that can easily become magnetized when a current is flowing and easily lose its magnetism once the current is withdrawn. So, and it has to continue like that over and over in split seconds. So you need something that can easily be magnetized and easily be demagnetized. And a material that can easily be magnetized and easily demagnetized is soft iron. So what we'll be using there is a soft iron as the core for the primary and secondary coil, which means the answer to this question is in option D. Now, you can practice to become even better by using the Exam Fun app, an app that is both exciting and rewarding, in the sense that you get to solve questions on any subject of your choice at different levels while you earn points, and it is rewarding in the sense that you can also make some money as you solve questions. So you can download the Exam Fun app today by clicking the link in the description box of this video and just enjoy as you learn and earn. And please do not forget, if you are not subscribed to the channel, just take a second to click the subscription button, and you can also hit the notification bell icon so that you get alerted every time we post a new content. And don't forget to share the video to help us reach a wide range of audience that are in need of videos like this. So please keep sharing, and if you have any question at all, do not hesitate to drop it in the comment section, and we promise to definitely attend to all of your questions. So just keep them coming. Now, this brings us to the end of day 35. The series still continues, so thank you so much for following the series so far. I'll be seeing you in the next video, so bye for now.